Welcome back. In the last lecture, we studied the rotational flows. The flow is said to be rotational when the vorticity omega, that is the curl of velocity, is zero everywhere. The circulation around any arbitrary loop in an irrotational flow is zero, provided that the loop is reducible. If an inviscid fluid is initially irrotational, then it remains irrotational at all subsequent times. We had seen that the governing equation for irrotational flow is the Euler equation given as del V by del T plus V dot del V is equal to minus G delta Z minus del of P by rho. The last two terms combine to give minus del of Z plus P by rho. Using the vector identity A cross B is equal to A dot del B minus A dot del B, we get V cross omega is equal to V dot del V minus 1/2 del V square for A and B is equal to V. Then we get from this V dot del V is equal to V cross curl of V plus 1/2 delta V square. And using this in the governing equation, we get del V by del T plus V cross omega is equal to minus del of Gz plus P by rho plus V square by 2. Thus, if the flow is rotational, that is, if omega is equal to 0 and the flow is steady, the left hand side is 0 and we get minus del of Gz plus P by rho plus V square by 2 is equal to 0. Thus, the Bernoulli equation holds everywhere in a steady irrotational flow and not just on a streamline. We can take point 1 and 2 for Bernoulli equation anywhere in the flow field and not just on a streamline as was required for general inviscid flow which were not necessarily irrotational. We again start with the last form of the Bernoulli equation and taking the curl of this equation, we get del omega by del T plus V dot del of omega is equal to omega dot del on V. The first two terms that are the terms on the left are combined to give you the substantive derivative of omega with time is equal to omega dot del V. This is known as the vorticity evolution equation. If omega is 0 initially in an inviscid flow, then d omega by dt is equal to 0. d omega by dt is equal to 0 means that the substantive derivative of omega is 0. And since omega was 0 to begin with, the value of omega is 0 at all subsequent times. That is, an irrotational flow remains irrotational flow at all subsequent times. The vorticity omega, which is the curl of V in a rotational flow, is 0, and the circulation gamma about any reducible circuit lying entirely in the rotational field is also 0. Let us consider a circuit as shown. the integral v dot ds over this circuit A, B, C, D, A going around counterclockwise is the integral of v dot ds over the arm ABC plus the integral over the arm CDA. We can reverse the direction from CDA to ADC to get the circulation about the whole circuit as integral integral of v dot ds over ABC minus the integral over the path ADC. Therefore, the integral about this path ABC is the same as the integral about ADC. Since we have taken path arbitrarily, this means that the integral of v dot ds between any 2 points A and C is independent of the path that we take. Thus, they depend only on the location of the endpoints A and C, so that we can write integral of v dot ds from A to C is equal to some function of C minus that function of A. Depends only on the locations of the endpoints, not on the path. This is possible only if v dot ds is d phi, that is del phi dot ds. That is, we can write the velocity as the gradient of function phi, so that the velocity in any direction is del phi by del s is equal to del phi dot ds. The function phi is called the velocity potential, and the velocity components in the various coordinate systems can be found out. The velocity components in rectangular coordinates are given by u is equal to del phi by del x and v is equal to del phi by del y. Also given in this table are the velocity coordinate u and v in terms of the gradient of the stream function psi that we did earlier. U is equal to del psi by del y and v is equal to minus del psi by del x. Similarly, we can write the velocity components in the cylindrical polar coordinates. We have done this for two-dimensional flows. These can be done for three-dimensional flows as well. The continuity equation is del dot v is equal to del u by del x plus del v by del y is equal to 0. The two components of Euler equations for the incompressible and steady flows are given below, and these are to be solved subject to boundary condition that the normal component of velocity is 0 at the wall. As was discussed earlier, we cannot apply the no-slip condition at the wall. If the inviscid incompressible flow is irrotational, the continuity equation above results in del square phi by del x square plus del square phi by del y square is equal to 0. This is obtained by substituting del phi by del x for u and del phi by del y for the velocity component v. In vector notation, this becomes del square phi, the Laplacian of phi is equal to 0. This is the well-known Laplace equation to be solved with del phi by del n is equal to 0 at the walls. Notice that this equation, though difficult to solve, is no longer coupled to the Euler equation. The flows in which we can define the velocity potentials and which are therefore called potential flows can be obtained simply as the solution of the continuity equation, which reduces to the Laplace equation subject to the boundary condition that the normal gradient at the boundary is 0. Physically, this means that there is no flow into the wall or out of the wall. The wall is impervious. The lines of constant velocity potentials are called potential lines of the flow. In two-dimensional, del phi, in 2 dimensions, d phi is equal to del phi by del x into dx plus del phi by del y into dy. And recognizing that del phi by del x is u and del phi by del y is v, we get d phi is equal to u dx plus v dy. Thus, the slope of a line of constant potential is dy by dx is equal to minus u by v. The negative of the x component of velocity divided by the y component of velocity. Recall that the streamlines, which are the lines everywhere tangent to the velocity, the slope of those streamlines is given by dy by dx is equal to v by u. Since the slope of potential lines has been found to be minus u by v, this means that the potential lines, which are the lines of constant potential phi, are perpendicular to streamlines, which are the lines of constant psi, except at the stagnation point. Thus, the streamlines are perpendicular to the potential lines at every point of the flow field. This is called flow net in some texts. And from this, we get del phi by del x is equal to del psi by del y, and del psi by del x is equal to minus del phi by del y. If we define a complex variable phi plus I psi, real part phi and the imaginary part psi, the stream function, then these two conditions are nothing but the Cauchy-Riemann conditions applicable for analytical function of a complex variable. Therefore, psi and phi, when they combine to form a complex variable phi plus I psi, this complex variable is an analytic function of z, which is x plus I y. This property of the potential and the stream function, which is given the name complex potential, is exploited in finding out the solutions of the Laplace equation. We will not do this here in this elementary course. To summarize the velocity potential and stream function once again, the definition of potential function is that V is equal to del phi. For the stream function, it is V is equal to curl of psi. The continuity requires the potential function to be del square phi is equal to 0. This requirement is built in into the stream function. The requirement of irrotationality is built in the potential function. But for the stream function, it becomes del square psi is equal to 0. So both phi and psi satisfy Laplace equation. Given below are the velocity components in the rectangular coordinates and in the cylindrical polar coordinates, same as before. Let us point out some interesting consequence of the fact that the velocity field of a potential flow is determined fully by the Laplace equation. First, the equation and boundary conditions are valid for both steady and unsteady flows, even though the time variation does not enter the equations explicitly. Interesting. If the boundary conditions are changing at time, the solution also changes with time. The rate of change of boundary condition does not affect the solution at a given time. This means that the solution is quasi-steady with every point in the flow field responding immediately to any change in the boundary conditions. This is the consequence of flow being incompressible, which requires that the disturbance propagate at infinite speed. The second interesting consequence is that the velocity field can be obtained independently of the pressure field, but not vice versa. We cannot solve the Euler equation to obtain the pressure field without knowing the velocity field. But we can solve the Laplace equation to obtain the velocity field without dealing with the pressure field. The Laplace equation for potential flow is purely a kinematic equation, while the Euler equation is a dynamic equation. Thus, the pressure gradient adjusts itself depending upon the inertia of the fluid measured by the density rho to give the desired velocity gradients. The third important property of the potential flow is that the Laplace equation and the relevant boundary conditions are linear, and therefore it is possible to build up solutions to complex flow fields using superposition of simple flows. Since the equation as well as boundary conditions are linear, we can take a number of elementary flows and simply add the potentials of those flows, and the sum would satisfy the Laplace equation. Let's next study some simple two-dimensional potential flows that could be used to construct more complex flows. The first flow we consider is a uniform flow where the velocity at every point is the same, v naught, and the velocity vector is inclined at an angle theta to the x-axis, so that the velocity in the x direction, Vx, is v naught cosine theta, and we give it a symbol capital U, and the velocity Vy in the y direction is v naught sine theta, which is given a symbol V. then phi, the velocity potential, is simply capital Ux plus capital Vy, that is V naught x cosine theta plus V naught y sine theta. And the corresponding stream function is minus Vx plus Uy. This is the flow net. The solid lines represents the stream lines, the lines of constant psi, and the broken lines are the potential lines, the lines of constant phi, constant velocity potentials. This is not very interesting in itself, but will be used for building up flows past bodies in 2 dimensions. The next flow we take up is the source or the sink flow. Laplace equation del square phi is equal to 0 in 2-dimensional cylindrical polar coordinates is 1 over r del by del r of r del phi by del r plus 1 over r square del square phi by del theta square is equal to 0. For axially symmetrical flows, the derivative with respect to theta are 0, and so this equation reduces to 1 over r del by del r of r del phi by del r is equal to 0, which is readily integrated to give a solution. Phi is equal to C1 ln r plus C2, where C1 and C2 are constants. Just like stream functions and velocity potential, we can add an arbitrary constant to any of the velocity potential and stream functions because it's only the difference of the stream functions or the gradient of velocity potential that matter. So we can set C2 as 0, and then the velocity potential is constant times ln r. This is the fundamental solution of Laplace equation for 2-dimensional axisymmetric flow. Now, this potential function gives you the r velocity component as del phi by del r is equal to c by r, varying inversely as radius, and v theta as 0. So velocity is radial outwards for c positive and inwards for c negative. So the velocity vectors are like these. For source flow, when c is positive, and inwards if c is negative. If we find out the total flow, total volume flow crossing a circle of radius r, we can obtain it by integrating the r component of velocity multiplied by r d theta over theta from 0 to 2 pi, and we get this value as 2 pi c. We can treat this total volume flowing out as the source strength Q, such that c becomes Q divided by 2 pi, and the velocity potential phi can be given as Q divided by 2 pi ln r as the velocity potential for a source of strength Q per unit depth. for two-dimensional flows. Using Cauchy-Riemann conditions, that is del phi by del x is equal to del psi by del y, and del psi by del x is equal to minus del phi by del y, we can obtain the stream function for the flow as psi is equal to q divided by twice pi theta. These are the streamlines that are plotted for q is equal to 1, that is for a unit source strength. This line here is for psi is equal to 0. We go around, we reach here. This is for psi is equal to 0.25. And we come back, we give the whole circle. We have this line which represents psi is equal to 0 as well as psi is equal to 1.0. These are the streamlines for a source flow. Velocity outwards for a source and the velocity inwards for a sink when the value of q would be minus 1. Let's next do what is called a line vortex or a free vortex. We have seen earlier that free vortex is the name given to a swirling flow in which there is no rotation of the fluid element. Two particles are shown with same orientation throughout the motion. The particles are not rotating about their own axis, but their different velocities in the two circuits, both the angular velocity as well as the linear velocity. The radial component of velocity Vr is 0 in this case, and the swirl component V theta is a function of r alone. So swirl component is not a function of theta. The Laplace equation for the velocity potential in 2D cylindrical polar coordinates reduces to del square phi by del theta square is equal to 0. And the fundamental solution is phi is equal to c theta up to an arbitrary constant, and which gives the velocity component v theta as 1 over r del phi by del theta as c divided by r. So the swirl component of velocity is inversely as r. Fastest at the center and slowest outside. We evaluate the circulation about a circular circuit of radius r in this flow, and we get the circulation is equal to twice pi c independent of the radius of the circuit. We have chosen circular circuit of radius r and find out that r cancels out and the circulation gamma is obtained as independent of 2 pi c. Therefore, gamma can be used as a strength of the free vortex, so that in the expression of the velocity potential that we have, c theta, we could replace c by gamma by 2 pi. And if we do so, the velocity potential becomes gamma theta divided by 2 pi. The radial component of velocity is 0. The swirl component of velocity is gamma by twice pi into 1 by r, c by r. by using Cauchy-Riemann equations, we can obtain the stream function, and stream function psi is minus gamma by twice pi ln r. So these are the streamlines and potential lines for a free vortex. The solid lines are the streamlines, the velocity tangent to the streamlines counterclockwise for positive value of gamma and clockwise for the negative values of gamma. The radial lines are the equipotential lines or the potential lines. Now, we have seen earlier that in rotational flows, the Bernoulli equation is applicable between any 2 points in the flow field. And therefore, for a free vortex, if we take a point 1 at radius r1 and a point 2 at radius r2, then the pressure difference P2 minus P1 is obtained as minus gamma square by 8 pi square into 1 by r2 square minus 1 by r1 square. If r2 is less than r1, then this quantity is negative. That means pressure P2 at the inner point is much less than pressure at the outer point. This is the shape of the pressure distribution. Pressure far away at r tending to infinity is shown by the broken line, and then the pressure decreases as r decreases. The vortices are very common in nature. They're found in oceans as whirlpools, in the atmosphere as tornadoes. They're huge vortices in the ocean. One of the largest one is located close to the Arctic Circle in Norway. It is estimated that 400 million cubic meters of water passes in a narrow strait during this event. This occurs regularly because of the lower pressure towards the center of this vortex. The water level decreases, so it produces a kind of a hole. This is an underwater view of the same vortex. What you see here is an air cone that seems to be pointing downwards towards the ocean floor. In the atmosphere, these whirlpools appear as tornadoes. A tornado is a violently rotating column of air in contact with the ground underneath a cumuliform cloud and is often visible as a funnel cloud. The pressure is very low in this funnel, and so it sucks the debris, cars, and human beings up. The intense low pressure caused by the high-speed wind and the rapid rotation of water vapor in the air condenses into a cloud droplets due to adiabatic cooling. This results in the formation of a visible funnel cloud or a condensation funnel. So let's summarize the three basic potential flow solutions that we studied so far: a uniform flow, a source flow, and a free vortex. we will build up the solutions of more complex flows from these basic flows in the next lectures. Thank you.